Still foggy outside? Sunshine is predicted sometime today, maybe 4 o'clock, just before it sets. It's going to be one of those times that it was nice having some sunshine yesterday. And let's see, do you want to watch that there, please, in the side, Bendy? Stuff on the side. I'm leaving the computer there, so you're going to have to adjust. Now, in terms of the homework I handed back, the homework was a matter of trying to give credit for the additional work that folks did who did all the problems that were assigned, so I gave those at a 2. If you did half the problems assigned and did well on those, I gave a 1. What mostly you're concerned about is whether or not there's a statement about the setup on your paper. If it says good setup, nice setup, what I'm saying is you've identified the variable, you've written the equation, you have provided the appropriate form of solution. That was critical in this set of problems. Many of you need to look at those papers and determine if I have this question for you. Let x equals question mark. And if I keep addressing that repeatedly in the problems, and I tended to look at about 5 of them, it means I'm not satisfied. If you wrote your solution to the equation, but you did not solve the problem in the sense answering the question that was asked, you didn't address the question in the problem, then that again is not adequate. So I wanted an identification of what the variable represents. I want an equation, I want the solution to the equation, and then I want you to answer the problem given originally. Now, some of you did a very nice job of doing that. Others of you, I think the extreme case was a paper where hardly an equation was written and just answers were given. Well, that's not the nature of what we're trying to do. It's not just finding the solution to 2 numbers that add together to get 11, for example, and one is 1 less than the other, and you sit there and think through the problem and say, gee, it has to be 5 and 6. That's not what this is about. You're trying to identify a variable, you're trying to set up an equation, and provide the solution. So that is the information regarding the homework papers, and I hope as you look at the feedback given, you understand what is indicated. If there are questions about that, then you need to see me and talk about it. And just leave the papers back there this time. Somebody comes in, then they can pick up their paper that way. The homework from yesterday involved taking formulas and solving a formula for one letter of the formula. And we tried to illustrate that on the board, and I was a little bit rushed at the end. I felt badly about that. But in order to cover the complicated type of problem, I felt it was necessary to finish it. And in particular, today on my voicemail, email request list was problem 62. So let's go to page 125 and look at number 62. Debbie can make the cut there. And this is a problem very similar to what we did yesterday. Now, I did it for a cylinder. Does somebody recognize the figure related to this formula given that particular formula? What is the shape? That's not the cylinder, it is the cone. So as in ice cream cone. So you can think of an ice cream cone as being 1/3 the volume of a cylinder that would contain that cone. If that makes any sense. So it's 1/3 pi r squared h. And in this particular problem, again, as we come back to the problem, it indicates to you that you're going to solve for h. So first, let me write the problem up here. It's 1/3 pi r squared h. This is number 62. And what we are asked to do is solve for h. You want to isolate this part right here. Well, in a sense, you could argue, divide everything by the coefficient. Now, typically, we think of a coefficient as being a numerical value. In this case, I could think of the entire remaining 3 factors as being a coefficient. So I could just say divide everything by 1/3 pi r squared, both sides. My suspicion is that may not be the most effective way to explain it. So I might argue if I multiply both sides by 3, And you can do it in parts. That is, you're going to get 3 times the volume then is equal to pi r squared h. And I have not shown that the 3 times 1/3 is 1. I am just making that clear from what I've done. Then I have pi in both parts, so I could think of dividing both sides by pi. That now gives me 3v over pi is equal to r squared h. And I still have what? R squared on both sides. So I can think of dividing both sides by r squared or multiply by 1 over r squared. That's going to give me 3v over pi r squared is equal to h. There are a number of remarks that I hear as I explain a problem like this to somebody doing it with some concern, some question, and it is trying to isolate out everything else as though they were numbers. And part of the difficulty, I think, for people doing this problem is to not see these just as if they were numbers and seeing them because they are letters as something different. But if I had instead 1/3 times 2 times 5 squared, so let me just illustrate what I'm saying here with 1/3 times 2 times 5 squared h, and I ask you to solve for h, I don't think there would be any problem to realize, okay, I multiply both sides by 3, and I get 2 times the 5 squared h, so I'll divide both sides by 2. So as I do that, doing it in pieces again, I would get 3v over 2 is equal to 5 squared h, divide both sides by 5 squared, and I have the same type of solution. And this brings up a point I'd like to make. If you have trouble with the symbols, replace them with numbers temporarily and ask, what would you do if they were just numbers? And then procedurally, try the same thing. And in some ways, Debbie, this goes back to the comment you made yesterday. Debbie had related the uncomfortable feeling of doing things with symbols like they were numbers. And it still is a sort of an awkward feeling no matter how many times you've done it and whether you've had the course. You know, it still may be an awkward feeling. And again, as I reflected on that, sometimes it's best just to replace things with numbers and say, well, gee, what would I do if it were a number? And I wanted h by itself. Then do the same thing to the letters. And hopefully that will clarify for you what has to be done. That's number 62. Any other questions on that from you in here? Yes? 64, which is right below it, so we can cut to that. Number 64. Okay, let me write that on the board. Number 64, we have ax plus by is equal to c, and I want to solve for y. Okay, as we cut to the board. First, I want you to realize that this expression is given a name. Ax plus by equals c is a linear equation in 2 variables. It is the generic version. Okay, ax plus by equals c. And that is standard form. Now this problem could be seen innocently just as one of those homework problems where, okay, I've got to solve for another letter. This one is very important to focus on. What I'm going to do here goes in your sort of personal notebook. Know this. Don't forget it. Forever. Okay? Forever. Particularly if you're going on to another course. Whether it's 90, 134, 130, anything in the hundreds level, this is worth remembering. Okay, so we have the term with y by it. I want that by itself. I want it isolated. So I'm going to write by is equal to c minus ax. So far okay? I, in essence, added negative ax to both sides. Then I am going to go ahead and multiply by 1 over b, or you may feel more comfortable saying what? Divide both sides of the equation by the letter b, and I am doing this with one of the properties of equality. So if I do that, I next see c minus ax over b. Otherwise, just draw a line under both sides of the equation and divide by b, putting the b underneath. Now I'm going to rewrite this right side in a way that you typically would not do in arithmetic. Otherwise, we have a common denominator. Now I'm going beyond what the solution might be. At this point, you could argue we are done with the problem. But I'm going to go a step further. That is the same as c over b minus ax over b, correct? Now, you don't often do that in arithmetic. You spend all your time getting what? A common denominator and then combining everything and stopping. I'm working in reverse. But I'm not done. In the form I really like this, it is going to be y equals negative a over b times x plus c over b. I wrote a over b, the negative a over b, as a coefficient of x. Now, in this form, I had a product. Here, the coefficient is negative a over b. Okay? Now, this form, solving for y by itself, is given a name. The slope-intercept form of a linear equation in two variables. Now this assumes something we haven't talked about. But as I look at an equation in two variables, coming back to the top part here, I could have an x and a y. And let me just illustrate this because I'm looking ahead to something. This is a type of problem that we talked about a moment ago. Two numbers add together to give 11. Now, I was talking about 5 and 6. Now, if I know more about the numbers, I can say let x equal a number. And then I'm going to say x plus 1 is the second number. And together, they add together. That's a bad use of together twice. But if I combine them, then I'm arguing that these two combined together will give 11. So when I simplify, I get 2x plus 1 is equal to 11. 2x is equal to 10. X is equal to 5, so my numbers are 5 and 6. Now that's a problem you did in homework, that style of problem. I can argue generically that I can have two numbers, x and the second number y, and add them together and I can get 11. Example, 3 and 8, 2 and 9, 1 and 10, 4 and 7. And if I allow for positive and negatives, I can say 12 and negative 1. The number of possible combinations up there is infinite. And I talk about pairs of numbers that work. So this problem, I had a single number that worked with the conditions I imposed. This would have infinitely many solutions. Example, the pair I'm going to write in parentheses, and I'm going to put a comma between the pair. So things like 5, 6 work, but so do what? 3, 8, 1, 10, and so on. Infinitely many. Now, if you have the background, it is assumed, that is assumed, you have graphed pairs of numbers. We do it in Math 10, we do it in 20, and it's assumed as a background in here. You would be aware that we would graph these on a coordinate system, and what's going to be true about this is that the solutions, plural, will be on a line called the graph of the equation. That line is going to have a slope, just like a ski slope, just like the slope of a roof. And that slope is given by the coefficient of x. Now, Debbie, thank you. Debbie knows where I'm heading. This coefficient right here, this negative a over b, is going to be the slope of that line. And then that line is going to meet the vertical axis, and that's going to be called c over b. slope and intercept for the graph of this equation that involved an infinite number of pairs of numbers. Okay, that is a whole chapter in its own right. But with your background that you should have coming in here, that's a neat problem. And I hadn't anticipated talking about that, but when I look at stat, and we come in as we're going to next week, the end of next week in the stat course, I'm going to come back and nearly have to readdress this entire comment for them because they had it and don't remember it. And they had it a lot and don't remember it. This is one I want to burn into your brain and leave there forever. Slope-intercept form for the equation of a line. You will see it on the next, well, see, you may or may not see it in the first test, probably not. But you certainly will see it during the semester in one of the tests and in the final. This is a biggie. So thank you for the question. That was delightful. I hadn't planned on that, but this was a big one. Yes?
I have a question on any of these problems on here. If you have a problem that has a fraction, you can always multiply the denominator on both sides. That's one way of doing it.
Yes.
There's also another way of doing it, right?
Okay, let's come back to 62 on the left here, Debbie, in answering Laura's question. The question was, if I have a fraction, can I always just multiply by the denominator? Yes. I hadn't voiced my solution in that particular form. I had said I can multiply both sides by the reciprocal of 1/3, which happens to be 3, which also happens to be the denominator. But if, for example, this had been 2/3, or let's take the volume formula for a sphere, where I have 4/3 pi r cubed. That's the formula for the volume of a sphere. My point is, if I didn't have 1/3 but had 4/3, I could then think of it as 1. Multiply everything by 3. Or multiply everything by 3/4. And that gets rid of that coefficient totally. Or divide everything by 4/3. Okay, I'm not reading the recognition I want on Laura's face. Okay, Debbie, we're going to go to just this little corner here on the end of the board with camera 2, and then I'll go over there. We'll leave this one. If you can come back up to where you can see 62 here with camera 1. There we go. Bring that in, and then I'll just leave that up there, and I'll go over to the side. What I was trying to say in a verbal form, and it didn't seem to be communicating well, partly because I suspect there isn't a comfort level with that formula, which is the formula for the volume of a sphere, like a basketball, baseball, the globe. If I wanted to get rid of the 4/3, what Laura is asking, can I just multiply both sides by the denominator? Well, that'll certainly get rid of the 3. So if I do that here, I'll have 3v equals 4 pi r cubed. And if I want to isolate r cubed, then what do I still have to do? Divide both sides by 4. Another approach is to say, well, let's multiply both sides by the reciprocal of the coefficient here, the numerical coefficient. Well, the reciprocal of that is 3/4. So I could say immediately 3/4 times b is going to give me pi r cubed. That's a little more efficient. Or I can say I'm just going to divide both sides by 4/3. Understanding that if I divide by 4/3, the 4/3 goes out on the right side. Now what am I left with here? An implied quotient which says take v, divide by 4/3, which is going to give you 3/4 v. But you have choices. Is there one right way? No. But is there any need to clarify that further? Does that answer the question for you, Laura? Okay, anybody else there? Okay, other questions on what we have on the board or on another problem? Because I still have one from my voicemail email list. Any other questions from you? Okay. Debbie, let's cut back. Oh, thank you. you. Okay, there's the 575-6759. I don't know if you intended that, but if that was the case, that's the number you can call in if you have a question you want to address, and we have to wait 20 seconds because they haven't seen it yet. But on simulcast, they'll see it shortly, and they can call in. But I'm going to go back to the document cam now. Aha. I threw you a curve, huh? Okay, that was 64 that started all this, which was a very nice question. And it's one of the things that as we do a problem, I will oftentimes use that as a springboard to cover something very important. 17. Is that mine or yours? Okay, that's yours. Here I thought I was getting a call, and Debbie gets the call, just like at home. Okay, 17 is where I'm going to go next. And that problem, as soon as I can get it up here, I'm trying to do this off memory. I left the page that was involved here sitting on my home office desk at about 6 o'clock this morning. But 17, let's try going to that, is the dirt formula. Okay, this is the dirt formula. D equals RT. Like pert, the shampoo without the E, so we have dirt. Well, this is a formula for distance, rate, and time. And it's a very classic one. This is one we cover in Math 10 as one of the formulas. Distance equals rate multiplied by time. And then you're given some information here on this, that D is 100 and T is 2.5. So what's implied here? You're going to solve for the remaining letter. So if I look at what space I have maybe up here on the front board, this is number 17. I have the formula D equals RT. Now, what we're doing here, as we jump to, I gives Debbie time to make the transition, we have the request to solve for R, in essence. You understand you have two choices here. One is to substitute the 100 into the problem, have the R, and I think the other was 25? 2.5, thank you. And this should be on the same line. That's looking a little bit too much like a what? An exponent. I don't like that. Let me try to get that in the same line so there is no intent that that is R to the T. If you do it this way, the 2.5 typically would be written where? In front of the R. That would be better form. But nevertheless, you would be inclined to just divide both sides by 2.5 and argue that R is 100 over 2.5. And then if you want a quick solution, you can ask, what would be R if we had 25 before? But you have 1/10 of that, so it's going to be 40. What is the alternate to this? Well, look at this immediately and say that R is going to equal D over T. And then you've solved for R first, now substitute, and you're there directly. And you get down to this immediately. But that's a choice you have. Now, the answer we have yet to write. Technically, I would tend to write the R on the left side and put my answer down there at R equals 40. Any question on that? And we have allowed time, I think, even with the delay, for people to call in if they had a question this morning. Yes?
Why just I got rid of the decimal when I just multiplied by
Okay.
10, so.
I didn't even think in terms of that as an alternate. Okay, I'm up here, and I don't like the decimal. So what will I multiply both sides by? 10, and I will get 1,000 equals 25R. Divide both sides by 25, and R equals 40. That's another alternative. Good point. Any other choices there? Okay. Any other questions? This obviously was not the difficulty level of the word problems for homework, because the questions are much easier, it seems, today. Okay, well, you do the pass and fold, pass. That's not commutative. You can't pass, then fold. You have to fold, then pass. And we get them up here towards the front. That would be appreciated. Okay, and what I was doing this morning when some of you came in and you heard the computer playing the video, I was going through and making the links for the video tutorials. And all the links are up now on the video tutorials for Math 70 through the first 5 lectures. And I was working on the 6th lecture, and those are posted, available, and not necessarily always with exactly the heading you might search for, but if you just scroll down the list of video tutorials, you can maybe find something that you were hunting for, even if I didn't identify it exactly in the way you thought. So, for example, on properties of the real numbers, I did properties and I did real numbers and cross-listed. But if you were thinking of number properties as opposed to real number properties or properties of real numbers, then number properties is not a listing I have. I had to draw the line somewhere. But let me know if those are working for you and if they are helping. All 5 lectures have now been, I guess scanning is sort of the word. What I do is I look at the content and then I try to identify a break point, and I'm taking about 1.5 minute intervals as I'm scanning through 60 minutes of presentation. And so far, then when I put them on the internet yesterday, I try to check each link, make sure it is functioning and where I want it to be. So if you have feedback on those or anything, it would be appreciated. We are moving on today, and Debbie, I'm going to go to eventually the side board. I'm going to ask you to return to Greek mathematics with me for a moment, so we're going to go to that pretty soon. And Debbie, once you get that camera, I'm going to have to go over towards the center of the desk again, so we'll just pan together, right? Okay, or something close to that, and I got ahead of you. The new section is called Ratio and Proportion. And there are so many things that can be said about this beyond what are in the text. But ratios and proportion. And there's the title on the book, Ratios and Proportions. There are various proportions that we think about and ratios that we think about. For example, one of the most common ratios that we have is a percent. It's something over 100. That's a ratio. A ratio is clearly a fraction. A rational number is a ratio. When we talk about ratios and we talk about applications, we oftentimes have units. So what is the ratio, for example, of 2 different objects that you've weighed in pounds? So I might think of the problem that I did this last couple days that comes to my mind. There was an interesting ratio, and it's one I shared with Debbie as we were talking yesterday. I had been defragmenting a hard disk, hard drive, on the laptop we use for presentations in here. It was at 48 hours when I stopped it. Okay, 48 hours into a defrag that had not stopped, and I needed the computer. I thought it was going to take at most 5 hours. Bad judgment on my part. So at 48 hours, you get to the point where you'll risk nearly anything, including trashing the hard drive. I pressed the start button long enough to stop the process, and then I went into a little fervent prayer. Please, deities, don't destroy the work that was there. And as I then called for help, I have a very nice helpline. It's a former student who's become a very close friend. And so I called Mike and I said, Mike, who's a person up in the Rohnert Park area whose responsibility is in system administration for an AS400 system, an IBM, and does a lot of work with laptops and Windows, and he said, try the safe mode. Well, safe mode basically takes you out of Windows into a sort of a Windows Lite, very modest Windows. And I then did the defrag, and it took 48 minutes. Okay, now you play that for a moment. 48 hours, 48 minutes. Which would you rather do? And what's the ratio now? Can I compare 48 hours to 48 minutes? No, because the ratio would be hours and minutes, and they aren't the same. So if I'm going to compare the ratio is really 60 to 1. How many minutes are in the 48 hours? 48 times 60. Over the 48 minutes it took to do in safe mode, so the ratio was 60 to 1. That's a ratio problem. And I needed to combine so that the minutes were to minutes rather than hours to minutes. Now, there are other ratios we do where you have the units differently. You do double nickel on the freeway. You don't, but we'll believe you do. 55 what? Miles over 1 hour. That's a ratio. Now, there we don't do what? Keep the units the same. And so we call it miles per hour. But ratios typically have the units the same. That's the first comment about ratios. You use a ratio every time you do a percent. A ratio is a common fraction. Now, proportions. If I have two fractions I set equal, we call it a proportion. Again, two fractions equal, we will call a proportion. I want to cover that in more detail in a moment. But I'm going to go to, in your text, a very typical looking equality as it's done. Let's go to that, Debbie. A over B equals C over D. That is a proportion. Two fractions equal to each other. But I also want to talk about something else with proportions called proportional thought. Now let me give you a problem using proportional thought. Okay, I'm trying to think of the example that would be good today. If, in the fog, it was foggy this morning, and I assume modestly so yet, if in the fog you were driving sensibly on the freeway and doing 30 miles an hour, how many hours would it take you to go 300 miles? 10 hours? Again, if you're doing 30 miles per hour in the fog, how many hours will it take you to go 300 miles to get to LA? 10 hours. That's a proportional thought problem. And we do those when we buy things at the store, we do homework, and we say, it's taking me 5 minutes a problem. How many minutes will it take me to do 10 problems? 50 minutes, proportional thought. Now those are easy. They get hard when you say, it's taking me 3 minutes and 45 seconds to do every 2/3 problem. How many minutes will it take me to do 4.5 problems? You don't run that one in your head very easily, correct? But proportional thought is that process that allows you to do the type of problem again. 30 miles per hour, how many hours to go 300 miles? You answer 10 hours, you're doing proportional thinking. Proportional thinking is a very important characteristic of thought process. And it's one that if the numbers get more difficult, we shut down our intellectual process and can't do it in our head. Okay? Example, you're doing 60 miles per hour. How many feet do you go in a second? It's the DMV exam question. Anybody? 50 miles per hour. I don't know if you heard the comment. It's a multiple choice question. What are my choices? I think they actually do 60 miles per hour, probably, and it's 88 feet per second. The idea is if you've looked aside 1 second to answer your cell phone and somebody just happened to be rear-ended ahead of you, you're into their bumper also. And they then admonish you to not use your cell phone in spite of the multiple choice characteristic of the question. See if you get your license. Now, I'm going to go to the idea that's expressed in here on the book in the follow-up to the proportion. And as we look at the document, Cam, it says AD equals BC. Now, that is being referenced as a cross product. I'm going to come back to what is presented in the book as a ratio in this form. A over B can be written A to B. Now, in early Greek mathematics, when they talked about two fractions being equal, they said A is to B as C is to D. Now, that was their version of what we have in the document, Cam. Remember what we had? A over B equals C over D. Back to the board. This was the way the ratio was written. They didn't use an equal sign. They didn't have an equal sign. They didn't know how to write fractions. So they tended to say A is to B in English as C is to D. But I'm going to at least use this much. Now note, these two values are at the end of the proportion, correct? They're referred to as extremes. And then these two values are in the middle of it, agreed? And the middle was like what we call means. Thank you. I'm going to need that little bit there to get means written in. And the way the early Greek mathematicians wrote this was the product of the means equals the product of the extremes. The product of the means equals the product of the extremes. Product means to do what? Multiply. So the product of the means, which would be BC, is equal to the product of the extremes, which is AD. So we would say AD is equal to BC back to the document camp. And isn't that the same statement? Now, if I write this as two fractions equal to each other, which is also a way of looking at the proportion, then note the A times D is sort of crossing, you know, a bit like the railroad crossing sign. And then you cross the other way. So I can think of an X going through there. And so that's where we get the cross product. Now, what does that have to do with proportional thought? Okay, let's come back to the type of problem we were talking about. If we said, let's see, 3 pounds costs $5, then how much for 9 pounds? I don't like that. 12 pounds. I want a different number. 12 pounds. Then your answer is going to be what? Just from thinking, without resorting to algebra. What's your answer? $20? Agreed? So you're going to argue that 3 pounds for 5, you're buying 4 times as much, so it should cost 4 times as much. So your answer, using proportional thought, is $20. Can we set this up as a proportion? Okay, if I'm going to do it as a proportion, now this is solution by proportion. You tell me what I want to write first. Anybody? What am I going to put here?
The 3 pounds over the 12? No.
Okay, 3 pounds over 12 pounds, because I'd like to do what?
Same unit.
Keep the same units. Very good. So my 3 pounds over 12 pounds, and then what?
Equal
Mark
to
the dollars
20.
over.
Then I have $5 over what I don't know. X. Okay. Or I could have said 12 pounds over 3 pounds, and then there are a variety of ways of doing it. But then, if I just think of this being like an X, the units cancel, because I'm talking about X dollars, $5, I'm talking about pounds over pounds. I'm really saying 3 over 12 is 5 over X, and then I can cross multiply. 3X is equal to 60, and X is equal to 20, and I have my solution. Okay, just sliding just a bit. There we go. You get the idea? Now that's straining at that a bit because, my God, we could get it without doing all that. Why go through this? Well, if I change the problem ever so slightly, and instead of saying 3 pounds costs $5, I might have said, as an alternative, 3 1/2 pounds cost $5.12. How much for 10.5 pounds? Now, are you going to do that one in your head as easily? No. Very clearly, this goes beyond most of our abilities to run it through our mental process without doing something in between. So we'd still do what, though? 3.5 over 10.5, and then I have here 5.12 over x. Now notice the same type of solutions involved here, but the numbers are much more difficult. Now, if I rigged this properly, and I did, what could you do to the left side? You're working too hard. More obvious. What? Okay, say it again. Cancel what? Not enough. I want to cancel more than that.
Oh.
Maybe I didn't.
Oh, the 5 into the 10?
No.
Do you see 1/3 here?
No.
3.5 goes into 10.5 3 times?
Yeah, that's what I said. If you cross out that 5.
Is that what you said?
Yeah, I said do the 5 into the 10. If you did that, wouldn't that be, the 5 would become a 1? And the 10 would become, no?
No.
Now, you can't take the 0.5. You can get 3.5. This reduces to 1/3, so my answer is $15.36. Okay, you didn't like that. 3.5x is equal to 10.5 times 5.12. We're okay with that? Then what am I going to do? No. I'm just going to divide first. I know you want to multiply that garbage first. I don't. Then 3.5 goes into 10.5 3 times 512 is 1536. So the answer to this is x is equal to $15.36. Well, that didn't quite go. I mean, when you rig problems, you hope that you're rigging them in such a way that people appreciate it. You didn't.
How did you see the 1/3? I don't get it. I don't know.
If I gave you $3.50 today and gave you 3 times that much tomorrow, how much would I give you tomorrow? Okay, $3.50. 3 times 3 is $9, and then 50 cents times 3 is $1.50.
That's
9 and $1.50 is $10.50,
Yeah.
which is 10.5.
Uh-huh.
That's how I got it. Think about this, okay? It'll come to you. Tonight you're going to say, oh, that's where it came from. We do a whole unit in Math 10 called Dimensional Analysis. And it's done again in Math 20, providing an approach to doing proportions without algebra. And if you didn't see that, then okay. Well, going on a little bit further. Where does this get used in a more serious way? Well, I'm going to come back to one of the problems that you're going to be doing. I think, let's see, will you look, it's either 34, 64, or 44. And that's telling you nothing. I'm going to leave this on the board, and I've got to search for the problem. I had a mental note of what it would be, and let's see what I have. Okay. Let's try 44. Problem 44. Nah, not 44. Let's try number, yes, it is 34. Okay, Argyle Lake, 34. Now, one of the things that was brought up yesterday, in one of the comments, we have some comments that occur after class oftentimes. And one of the comments was, gee, there was a number about in Anchorage, Alaska, that there was a 1,000-mile race. And you didn't get to use the number. It's like you've been cheated. I mean, if the numbers are there, you should use them. That's why the numbers are there. Well, on problem 34, it says May 13th. Who gives a rip that it was May 13th? It could have been May 31st for all you care. It's not really relevant. The fact that it was Argyle Lake, it could be Turlock Lake, Modesto Reservoir, doesn't matter. Now the fact that there were some fish there does matter. Now let's see what we have. Now the next phrase is tagging fish. Now if you've played tag, this probably doesn't mean the same thing to you. So the question, what does tagging a fish mean? Label it. I'm sure people have one. Okay, you get one of those labels, and you put a label on the fish.
Well, you push it into them.
Okay, it's a little metal tag sometimes, color-coded or something, clipped onto a fin, and then you put the fish back in the water. It's humane. Now I'm getting this look of how unfair to tag a fish. You're going to identify this fish. So you have tagged 420 fish, and you throw them in the lake. So there's 420 fish tagged to the total population of the lake, meaning the number of fish in the lake, including the tagged fish. Got it? You don't know how many fish are in the lake, but you know the number of fish in the lake, 420 of them now have a little tag on them. Now the next part. A few weeks later, a sample of 500 fish has been selected. Let's go to the book. A sample of 500 fish. Now the question is, what kind of sample? Well, technically, a random sample. Now, I'd like getting random samples with you go out with a rod and you throw bait into the river or lake and you hope to catch a fish. That's not how they do this. How does Fish and Game go about getting a random sample? They first make a very interesting assumption. The fish will mingle. A tagged fish will not be in some way isolated. You're tagged. You can't come. No. The fish will just swim around, and there's no way that a fish being tagged is kept out of the school of fish. School fish? You know, they swim around together. Okay, then Fish and Game goes out. They perch a boat. Perch is a nice phrase for fish. They perch a boat in the middle of the lake. They drop down electrodes, and they zap the lake, and fish float to the surface, momentarily stunned. This is still, the fish will live. Okay. You've seen Crocodile Dundee, where he just throws the dynamite into the river, and then the fish come up, and that's the way he fishes. Well, this is similar to that. You shock the fish temporarily, and now 500 fish rise to the occasion. Of those fish, how many are tagged? 9. Finally we get to this. So, 9 tagged out of how many? 500 that were tagged total. And so the argument is that should be in the same ratio as what? The 420 fish that were tagged to the total population X.
So should it be 500 not tagged? 500. 500 total, right? And the 420 was the tag.
Thank you. Just a minute.
Yeah, the
I didn't
420.
do that properly. My apologies, because I was trying to get tagged to tagged, and you're right. It was 420 tagged total, because I want my ratio to have the same units. And here I have what? The 500. That's fish. Now, in my sample, so I had sample, total. By the way, was it technically correct to do what I did here? Yes, because you can do what? You can exchange the means, or you can exchange the extremes. That's one of those little rules that works with fractions. You get the same cross product. Well, with that in mind, I can solve for x. Okay. Now, for those of you who have any background in math, 10, this is a simple closed curve unit on the Monte Carlo technique of probability. That's what we're doing here in sampling theory. The tag, cancel. Agreed? And now what will you do? 9x is equal to 500 times 420, and you're going to let x then be isolated, and you have 500 over 420, and I hear the request, why don't you just multiply first? Answer, maybe I can reduce some fractions. Because you're not supposed to do what? Use a calculator. I gotcha. So anything you can do to make life more pleasant. What do you note about 42? It can be divided by 3? So you can reduce that a little bit. It's still not a nice problem, but it's better than it was. Okay, you're going to find x. I don't know what x is here, but we're going to find that for the answer. I'll leave that on the board. That's using proportions to solve a problem, and that's one of the style that you will do in your homework. Now, the kind of problem where I talked about taking the ratio of two numbers, in the first set of the problems here, the first subgroup, we're looking at page 131. And we have 16 miles to 48 miles. If you want the ratio, you say 16 to 48, and you get 1 to 3, and you're done. Again, I'm looking at number 2. As you see in the screen, 16 to 48, 16 over 48, the miles cancel, the dimensions cancel, and so you're left with 1 over 3. You do reduce ratios when possible. Any question there? Okay. Then, I'm going to come off there for just a moment. There is an interesting little statement about proportions that, how do you know a proportion is true? That's the question. Well, the cross product must end up in something that's equal. Let's look at the following problem. Okay, I'm hoping your arithmetic is improved in the last 10 minutes. I'm being a little bit sarcastic there. Okay, take the cross product. 4 times 21 equals 7 times 12. Is it clear you get 84 in each case, doing it in your head? 4 times 21, there are no carries, so that's easy. Now the 7 times 12 is harder because you have to carry a 1 when you take 7 times 2 and get 14. But you get 84 equals 48. 84 equals 84. Therefore it is true.
Can't you just reduce the fraction and see that 1/3 is
Okay. You are wanting to cheat. Debbie asked me, can't I just reduce both sides and see 1/3 equals 1/3? I guess my answer, Debbie, is with the last fiasco on reducing 3.5 over 10.5, we're probably safer multiplying. That's the smart-ass answer to that question. Yeah, if you can reduce both ratios to the same thing, then clearly if you have the same ratio in reduced form, then they are equal. But the usual acid test is to take the cross product and see if it works. Then we get to solve a problem such as we've done here in a moment. Now notice I'm doing the even problems, so I'm not saving you any work, I know. I'm going to get this down closer. Okay, let's go for that, Debbie. The top one, 49 over 56 is equal to z over 8. Okay, now, what's the suggested form of solution with what we've done? Cross product and then solve for the variable, correct? But in the spirit of Debbie's comment, coming back, well, you asked for this, let's come back to this. Do you see that you could reduce the left side to 7/8? Therefore, z is 7. Better put it back on the screen a little bit more. That was too fleeting. Okay, look at the screen. The left side becomes 7/8, so z has to be 7. I would prefer you take the cross product and solve for z. Getting the idea? this is not a bad set of problems. Most of what comes out of this is understanding that proportional thought is very important in mathematics and science. Much of what algebra involves, in a way, is avoiding proportional thought. Because under stress, proportional thought is voluntarily thrown out the window, and you worry about survival. Okay, so proportional thought, very important in a concept of thinking, but it's something that with algebra, through cross products, we can get around. The application I did with the fish problem is a classic one in proportional thought, and it is used very often in science and mathematics. So that is less trivial than it may seem. I have an assignment for you. Surprise, right? I mean, this is a little different way of giving the assignment. Okay, let's try and see what we get. Well, not quite dark enough. There, better? Section 2.5, I believe that's where we are. 1 through 33 odd, then 43, 45, 47, and then 59 through 62. The NC means no calculator problem. So 1 through 33 odd, 43, 45, 47, and then 59 through 62. I think you will find what we've done today should be adequate for you to solve those problems. Debbie, we started with Neil Diamond, and we're going to close, I assume, with Neil Diamond, but I'm not sure I should assume anything today. America is the choice here. So have a great day. We'll see you